Yesterday we learned an equation that describes for us the potential energy that exists in a stretched or compressed spring or elastic. We call that spring or elastic potential energy, and it's found by the equation 1/2 kx squared. Now, x stands for how much it's stretched or compressed. EP is the amount of potential energy. And K, this is what we want to focus on today, is the spring constant or the elastic constant if it's an elastic. Now, I told you yesterday that you can find the spring constant if you need to by using the equation K is equal to F over X. That's really a form of Hooke's law that looks like this on your data sheet, F is equal to KX. Hey, that works for us, and we'll continue to use that when we're solving problems if we need to. However, it's not the best way to find the spring constant. We have to do it when we're solving problems because it's the only option we have, but it's not the best way. And I'll tell you why it's not the best way. It will theoretically work perfectly every time. But the problem is, if we're off a little bit on our data for X, or we're off a little bit on our data for F, or we're off a little bit on both of them, then that can create an issue with the value of K. If we're off a little bit on both of them, then we end up being off quite a bit on the value of K. When we're actually measuring values, it's better to have multiple values and have a nice way to kind of average those values. Best way that we know to kind of average those values is to plot a graph. So ultimately what we're going to do today to find the value of the spring constant of a particular spring is to get multiple values for displacement, get multiple values for force, plot a graph with that, and then use the graph to get the spring constant. It's not what you're going to do every day in class when solving problems, but it is a better way. It's just not a viable way, or it's just not really an option when you're solving a problem where you don't have very much data. All right? So here's what the activity is going to look like. Every group is going to be given what's called a Hooke's law apparatus. That's this. It kind of looks like a retort stand in chemistry. You guys know what a retort stand is? Okay. It's not as heavy, it's not as big, but it kind of looks like the same thing, kind of functions the same way as well. We'll call that our Hooke's law apparatus. Can't really see this very well, but up at the top, there's a little hook that comes out from that, and hanging from that hook is going to be a spring. Every box of Hooke's law apparatus is going to have a spring in it. Now, every box should also have this, it's going to come in a different box. It's going to come in this little green box. It's called a mass tray. Now, on that mass tray, you're going to slide on these slot masses, these masses that are made especially for this mass tray. And you're going to hook this mass tray with various slot masses onto the end of the spring. And you're going to see what effect that has on the displacement of the spring. In other words, you put a little bit of mass, 20 grams on the mass tray, how much does it stretch? You put 50 grams on, how much does it stretch? You put 150 grams on, how much does it stretch? Make sense? That's essentially our apparatus right there, essentially our materials right there. Now, let's take a bit of a closer look at this, a zoomed in photo of the spring itself. Notice there's a ruler on the back of this Hooke's law apparatus. That ruler is actually quite movable. All you have to do is squeeze the back of the ruler with your fingers, and you'll see this when you get it. Slide it either up or down. What I want you to do when you hook your spring onto it is to slide the ruler up or down to the point when the bottom of the spring is reading 0. That's not actually perfect in the picture here. Okay? Ideally, this spring would be down a little bit further, or the ruler would be up a little bit further. Again, ideally, we want the bottom of the spring at 0. So in other words, as no mass is on the end of the spring, there is no displacement. Does that make sense? It's not stretched when you haven't put any mass on it. What are you going to do? Well, you're going to put that mass tray, right, that holds those slot masses on the end of this. And then you're going to put masses on that and see how it's affected. When you put masses on it, looks like this. Clearly, it's not reading 0 anymore. Looks like the bottom of that is reading at 3. So my displacement in this case, with whatever that mass is, right, Adam, would be 3 centimeters. Put a little bit more mass on it. Take a little bit of mass off. It doesn't matter what order you do it in. You start with heavy, go light. Start with light, go heavy. Go heavier, then go lighter. It doesn't matter, as long as you have at least 10 different trials of different masses on it. What kind of analysis are we going to do? Well, we'll deal with that in just a second. What's my problem here? What's my problem? What am I trying to do here? Yep. Trying to find the spring constant of a particular spring. Remember, we phrase our problem in the form of a question. So we're not going to say the problem is to find the spring constant. The problem would be, what is the spring constant of a particular spring? Okay, what is the spring constant of a particular spring used in the activity? Our variables, we got 3 variables: manipulated, responding, and control. What are we changing in this activity? Let's go back here for a second. Okay, as we perform this activity, what are we physically changing? What are we manipulating, Merrick? The mass on the end of the spring. Now be careful with that. The mass on the end of a spring is not an end in itself. It's just a way to get us to an end. What we're really changing here, Merrick, is the force on the spring. We're just doing that by putting mass on it. Does that make sense? So my manipulated variable, I'd probably give you mass if you put that down, but technically it shouldn't be mass, it should be the applied force. Oops, where is it? Here we are. Now I'm not going to tell you what the responding variable is. You can probably think of that, right? As I put mass on it, as I change the force, as I manipulate the force, what changes because of that, or what responds to that? Okay, you can probably think of that. Also think of a couple control variables. There's at least one really, really, really super important control variable that you can't miss this one. Okay? Ideally, we have 2 or 3 good ones, but one that's absolutely essential. Hypothesis, we're not going to make you do this time. It was the first time we were going to make you do it, but this time we're going to hold off until next time because of the problem. The problem is to find the value for the spring constant. A hypothesis should be an educated guess. Well, what kind of educated guess can you make when we're trying to find a number? Usually a hypothesis would go more with a relationship type lab as opposed to a number type lab. So don't bother with the hypothesis. Materials, okay, we already addressed the materials. Procedure, well, we've kind of addressed that as well, right? Set it up like this. Okay, make sure it's lined up with 0. Okay, put the mass tray on it, put a mass on it, see what the displacement is, put another mass on it, see what the displacement is, put another mass on it, see what the displacement is, and so on and so on and so on. Your table for data should look like this. You got your first mass, whatever the displacement that goes with that is. You got your second mass, and so on. Now, I've only got room for 6 different data points here. You want to have at least 10. At least 10 data points. If you got time, do 15. The more data, the better. Remember we said, perfect world, 1 force and 1 displacement would get you the spring constant. But it's not a perfect world, because if this number's off by a little bit or this number's off by a little bit, then so is this. The more points we have for f and x, the better. 1 isn't very good, although we have to use it when we're solving problems. 10 is pretty good. 20 is even better. 50 is even better. You're going to have to strike a balance there between what's better and what's convenient for time. Okay, probably 10 or 15 data points. Then you got to create an analysis table. We're not going to plot a graph with mass in it. We're going to plot a graph with force in it. So we're going to find the force by multiplying the mass by 9.81. Make sure it's in kilograms, then multiply it by 9.81. The displacement is still the displacement. I'll make sure it's in meters. We're going to plot a graph of displacement in meters versus force in newtons. And you're going to find that when you do that graph, it's going to be pretty darn close to a straight line. Now I'm going to show you something that you've never seen before. I'm going to show you a technique to find what the slope means. To find what the slope means from a graph that you've never seen before. You've never seen this graph before, x versus f, or displacement versus force. But we're going to figure out what the slope means together. At the beginning of the year, we did position versus time graphs, and you know that the slope of a position versus time graph means velocity, or the slope of a velocity time graph means acceleration. You know that. But you know that because I told you that. How would you have figured that out yourself? How will we figure this out, what the slope of this graph represents? Here's the technique. Now, we don't want to lose too much sleep over the technique, because this is more of a technique that we use in Physics 30 a little bit more. Okay, but if we can expose that to you and have you understand it a little bit, then by Physics 30 you're in a little bit better shape, right? Here's what we got to do. We got to get an equation from our graph. Now, that shouldn't be very hard, because the equation that describes every straight line graph is what? Forget about this. Forget about what variables are on there. What equation describes every single straight line graph, period? You know this from math class. Yes, but we're going to phrase it a little bit differently there. Yeah, y equals mx plus b. Now, watch what I'm going to do. My y-axis is displacement. It's displacement not delta d, but x. That's a little bit confusing, right? The y-axis is x. It's not x as in x-axis, it's x as in displacement. M stands for the slope. I'm going to write the word slope in. It's already confusing enough. If I don't write the word slope in, if I keep it as m, I'm going to think it's mass. It's not. My x-axis is force. So my y equals mx plus b is turning into x is equal to slope times f. The y-axis, or sorry, the y-intercept should be pretty darn close to 0. Theoretically, it should be exactly 0. So we'll cross that off. There is no y-intercept. I'm left with this equation that describes this graph. Now I want an equation for my equation sheet. What equation from my equation sheet has both f and x in it? Try this one. Right, same two variables, f and x. But I want to rearrange it to solve for the same variable. So if x is slope times f here, then we're going to say x is equal to f over k here. There's my equation for my data sheet. Now, here's the crux of it. It's not the hardest part of it. Okay, we're through that. But it's the crux of it here. Cross off x because it appears in both. Cross off f because it appears in both. We're left with the slope on this side and 1 over k on this side. So the slope of that graph represents 1 over the spring constant, which means if we want to find the value of the spring constant, which is the whole problem in our lab, we're going to just rearrange that, get 1 over slope. Google Sheets will split the slope out for you. It'll tell you what the slope is. All you need to do on your calculator is to flip it over. Take the inverse of the slope, and that should give you your spring constant. Don't worry about calculating the slope by hand. Okay? Just allow Google Sheets to do it for you. All right, conclusion. What was our problem? Conclusion usually relates back to hypothesis, right? Did you prove or disprove your hypothesis? Well, the hypothesis relates back to the problem, and we don't have a hypothesis here, so we'll go right back to the problem. My problem was, what's the spring constant? What's my conclusion? The spring constant is blank. How do you know? Okay? How do you know? And finally, your sources of error. Give me 2 or 3 good sources of error and corresponding suggestions for improvement. I had an issue with a group this morning in Physics 30, when we were doing an activity in Physics 30. And I like it when this happens. Somebody says, oh, we shouldn't fix this because this would be a good source of error. We'll mention this in our sources of error. And then they're saying, well, yeah, let's fix it. They fixed it before they did the activity. They recognized that it was a source of error, and they fixed it. Does that take away your source of error? No, just tell me in your sources of error, hey, this was a problem. this was a source of error. Instead of saying, I'll fix it this way next time, say, I fixed it this way this time. That's better, isn't it? If you recognize your sources of error as you go, as opposed to after the fact. So if you think of something as you go, don't leave it and say, oh, I don't want to lose my source of error. Fix it. And then tell me you fixed it, because I look at that as even better than just leaving it to save yourself a good source of error. Right? So what do you got to hand in for this one? Pretty much everything. Minus what? Everything minus the hypothesis. Yeah. Any questions about that?